again. This is the third lecture of fourth week. We're still looking at graph coverage criteria. What we did in the last lecture is we finally moved out of looking at code and testing of code using graphs. We started with design in the last lecture. I gave you the basics of what is the kind of testing which is done with design. The kind of testing that is done with design is called integration testing. We saw the classical view of integration testing, the various approaches to integration testing, what is tested and what is not. What we'll do today is we'll see how graphs can be used to do the kind of integration testing that we saw earlier. Specifically, we'll see what are the coverage criteria that we have already seen on graphs that can be used for integration testing and what new coverage criteria could be defined over graphs when we look at integration testing. So what are the goals for today's lecture? We want to be able to apply the graph coverage criteria that we have already learned, which is structural coverage criteria and data flow coverage criteria, to be able to do design testing. That is, to be able to do integration testing that involves software design. And while doing so, what will be the graph models that we will consider? The most popular graph models that we will consider are what are called call graphs. As we saw last time, what is a call graph? Well, there are several modules or components. The software is broken up into these modules, and modules talk to each other through interfaces. And when modules call each other or talk to each other through interfaces, the graph that models this is what is called call graph. The vertices or nodes of these call graphs are the various modules. Sometimes when I'm doing bottom-up or top-down testing, we saw that some modules could be replaced with test stubs or test drivers. So the vertices of this call graph could be either the modules or the test stubs or the test drivers. The edges are basically the interfaces, the various calls. What do structural graph coverage criteria over such call graphs deals with? It so happens that structural coverage criteria basically deals with calls over interfaces. You're basically checking if one module is calling every other module that it is supposed to, and the called module, is it working fine, right? And so on. And then what do data flow coverage criteria over such call graphs deal with? They deal with how data is exchanged between the interfaces that connects these two modules. Suppose it's a normal call interface where one module is calling another module. So the data is passed as parameters. The called module does its work and returns some data, right? So data flow coverage criteria deals with this passing and return of data across the interfaces. So we'll first look at structural coverage criteria, then we will move on to data flow coverage criteria over call graphs. We're not looking at graphs that correspond to control flow right now. We're only looking at graphs that correspond to call graphs. Sometimes while modeling call graphs, we might also have to model parts of the CFG. We'll see it through examples how that is done. So now, what do structural coverage criteria over call graphs deal with? If you remember, what are the various structural coverage criteria that we dealt with? We dealt with node coverage, edge pair coverage, then complete path coverage, which was infeasible. Then we looked at specified path coverage, prime path coverage, right? So what does node coverage deal with here? What are nodes in our kinds of graphs when we do design integration testing? Nodes are basically software components or modules. So node coverage would mean call every module that is supposed to be around. Right, so suppose I have a procedure that's a standalone procedure that is not being called by any other procedure or method, then it might as well not be there, right? So node coverage will make sure that every component that is there in the modularized software is indeed useful and being called by some component. What does edge coverage deal with? What are edges here? As we saw, edges for call graphs are interfaces. So edge coverage deals with executing every call at least once. So make sure that each call is executed at least once. So it basically tests for coverage to make sure that there are no unnecessary calls, unneeded. If there are calls that are never executed once, then edge coverage will not be met. And maybe it means that those modules can be removed. They are not needed at all, right? So edge coverage is a useful coverage criteria. Then it so turns out that other edge pair prime path coverage may not be very useful, because if you remember, the sole purpose of prime path coverage was to be able to handle loops in graphs. In call graphs, we don't have loops and other things that we worry about, so we don't consider prime path coverage. But if you remember the various kinds of testing that we looked at, top down, bottom up, Big Bang, and so on in the last lecture. So when I'm doing Big Bang integration, that is when I'm putting together all the modules that I have developed so far and testing the integrated way of working together, then I can use what is called specified path coverage as a structural coverage criteria to be able to do Big Bang coverage, right? So this is one kind of use of structural coverage criteria. What other kinds of call graphs could be there in software? In object-oriented software, there are what are called class call graphs. And now we can say, do we look at coverage criteria over class call graphs? But I would say that coverage criteria over class call graphs does not make sense at all. Why? Because individual methods residing within a class may not call each other at all. Classes are not executable objects. So what could be other kinds of graphs that are related to classes? Typical other kinds of graphs that come related to classes are graphs that deal with class inheritance and polymorphism and so on, right? So what we will do later in subsequent weeks, after we look at all the various coverage criteria, we'll spend 1 week where we will exclusively look at testing object-oriented applications. In that week, we'll revisit these class call graphs, and I'll tell you a lot in detail about how to test a large piece of object-oriented software for functionalities like inheritance, polymorphism, and so on. So there is this theory called class inheritance test order that people define to be able to do integration testing over classes, but we will not look at it today. We'll look at it after a few weeks when we dedicatedly look at object-oriented testing concepts. Right, moving on, when I do class inheritance testing in terms of coverage criteria, I could do the following. Consider this picture. If you look at this picture, there are 4 classes here, A, B, C, and D, and read this connection arrow as inheritance, right? So classes C and D inherit from B. B in turn inherits from class A, right? As I told you, classes are not executable, so I really cannot do in terms of testing anything for this inheritance. Instead, what I do is I consider objects that are instantiated for each of these classes before applying coverage criteria. So in this picture, I have depicted an object A1 that is instantiated for class capital A, object B1 that is instantiated for class capital B, object D1 for class D, object C1 for class D, right? So if this is the picture depicting an inheritance a hierarchy over a class graph, how do I apply structural coverage criteria over such an inheritance hierarchy? So it doesn't make sense to consider plain classes and apply inheritance hierarchy. I look at objects instantiated for each class and then apply inheritance hierarchy based testing. So when I do that, 2 kinds of coverage criteria make sense. The first kind of coverage criteria is what is called object-oriented call coverage. So we'll see what it says. It says the test requirement or TR for OO call coverage contains each reachable node in the call graph of an object instantiated for each class in the class hierarchy, right? So I go back, I look at this class hierarchy, and then what do I say? I say my test requirement is each reachable node in the call graph of an object instantiated for each class in the class hierarchy, right? So each reachable node should be covered. And the second one is object-oriented OO object call coverage that says that TR contains each reachable node in the call graph for every object instantiated for each class in the class hierarchy. So here this picture depicts only one object instantiated per class, but that need not be the case. There could be several of them. If that's the case, then I do what is called OO, object call coverage. So basically, in summary, what we are saying is that if I look at class inheritance graph that looks like this, don't consider classes plain because they're not executable. Instead, you look at objects that are instantiated for each class. When I test the calls related to objects in the call graph, one object per class, then it's called OO call coverage. When I test the calls related to objects instantiated in the class graph for each object in the class, then it's called object call coverage. We'll revisit, as I told you, all these concepts later in a week when we dedicatedly do object-oriented testing applications. Now we're done with structural coverage criteria. I would like to move on to data flow coverage criteria over design. As I told you, right, data flow coverage criteria is very interesting when I look at inheritance testing because it actually deals with the parameters that are passed and returned. Maybe that is a richer source of error instead of just checking for structural coverage criteria, which just checks is a module called, is a module interface called, and so on. It just checks whether it's called or not. Of course, that's also useful, but what is more useful is actually reasoning and testing for the values that are called and returned in each of these calls and returns. That's what data flow coverage criteria deals with. So data flow interfaces are more complicated than control flow interfaces. Why? Because values are passed, they obviously change names. We'll see it through examples. I might pass a certain value in the variable name X. It gets passed to the callee as a variable, let's say Y. Right? So they change names, they get assigned to different variables. And as we discussed in the last module, there are several different kinds of interfaces. I could communicate by explicitly passing parameters and returning values. I could communicate by reading from and writing onto a global set of variables. I could communicate by sending and receiving messages across dedicated buffers. So data flow testing has to be done across all these kinds of interfaces. And the other important thing is, remember, now definitions and uses of variables, as we deal with in data flow criteria, will have to run across modules, right? So a particular variable could be defined in one module and used later in another module. So we'll see through examples what each of these mean. So the focus for the rest of today's lecture, this lecture, would be to look at data flow coverage criteria, but specifically looking at data flow over call graphs as we use it for. So here is an example. Let's say if you look at the picture on the left hand side, let's say there is a method or a procedure A. A has some codes. I have not really written what the code is. Read these dots that you see here is some code that corresponds to A. As a part of the code that is written for A also calls another method or a procedure B with a parameter X. Right? When A executes and when this line of A comes into picture, what happens? Control gets transferred to the method or a procedure B, which is right here down there. And remember, A calls B with the actual parameter X and it's passed to B as Y, which is the formal parameter. Strictly speaking, X and Y are the same value, but they take different variable names. I need to be able to remember the fact that X and Y are the same values, but they take different variable names. X takes X in A and the same X is called Y in B. So A runs, at some point in time A calls B with parameter X, then X is passed to B as Y, then B executes, read these dot as some code that corresponds to B. I haven't really written the code for A and B because the focus now is to test for the interfaces, test for A calling B and B returning something, right? So B runs something, B finishes and B comes. When B finishes, the control is passed back to A and the rest of A executes and finishes. So here are some terminologies that we will use for the rest of the couple of lectures. So A is called the caller module, a module that calls another module. In this case, it's the module that it calls is B. B is called the callee module, which is the module that is being called by A. The call site is this statement, the statement in A where the procedure call happens. Actual parameter is x, this x that is passed as a parameter to b. Formal parameter is y, the parameter that callee b takes from the caller a. Interface is the place where control is transferred from a to b, and after b finishes running, control is transferred back to a. So what are the terminologies that we looked at till now? There's caller, there's callee, then there is call site, which is the place where the call happens or the interface is connected. Then there are actual parameters, then there are formal parameters, right? So now if you, one more terminology before we move on, if you go back to this figure, look at this actual parameter x, it's passed as x, and b, what does b take x as? B takes x as y. So we say x and y are what are called coupling variables. So coupling variables are variables that are defined in one unit and used in the other. And as we know, based on the kind of interfaces that we are looking at, there could be several different kinds of coupling. There could be parameter coupling. Example of parameter coupling is what we saw here. A calling B with X as a parameter and B returning it back to A with something else. Coupling could be in terms of shared data when modules communicate by reading from and writing to a set of global variables or shared variables. Or coupling could be in terms of an external device, right? You could have a database that resides in a particular database server, and then you say, I read data from that database server, and that could also deal with explicit coupling variables. But when we look at this particular module, I'll assume that parameter coupling is one coupling that we are looking at, and the abstract def use pairs that we will look at will deal mainly with parameter coupling, and in other cases also it should go through at a same level of abstraction. Some more definitions before we move on and look at an example. Remember, what is the focus? The focus is to be able to understand and test how data is passed across interfaces, right? So the focus is on interfaces. So if I go here, if I consider data flow testing for A and data flow testing for B, there could be a whole set of variables that reside in A, whole set of other variables reside in B, which I will do when I do normal data flow testing for source code. I'll test it for that. But the goal for today is to be able to test how A calls B and how B returns A. So what I do is I focus on the parameters that are passed and returned and the values that are defined and used around the parameters that are passed and returned. So that gives us the definition of what's called the last definition of variables, which occur just before calls to another module, and what is called first uses of variables, which occur soon after the module is called, inside the called module, right? So what is LastDef? Last definition is a set of nodes in the control flow graph of the caller module that define a variable x, and it has a def clear path from the node through the call site to a use in another module. So to better understand this, let's look at an example. So here is a caller method or procedure f calls another method or procedure g. So g is the callee. Let's say f has some code that goes like this. Again, please read these dots as some code that is there, but I am interested, I have put the statements corresponding to only fragments of the code that I want to focus on. So at some point in its working, f has the statement where it says x is 14, and after that it's def clear for x. X is not defined in these places where I'm pointing to, in these dots after x is equal to 14. And then f calls g of x with this value of x, and then control gets passed to g. What does g do? G takes x as a, it runs as g of a. So this x actual parameter is passed as a, which is a formal parameter, to g. The first thing that g does is to print the value that it obtains. So the last def of x was here, and the first use of x passed as a is in this printf statement. Is that clear? Please note that I don't consider the parameter passing itself as a use. So you could argue that this could be thought of as the last use of x in f, and this could be thought of as the first use of x as a coupled with a in G. But typically when we do integration testing, the point of parameter passing at the call site is not considered a use. What we consider is after it's passed by the called method or procedure, inside the called method or procedure, where is it first used. So this print a of x being passed as a is considered the first use of the variable x that is coupled with a. And now G, after it prints a, it executes a few more statements. At some point it defines b as something like this: b is equal to 42. Then it executes something. This bit after the definition of b is def clear for b, and then it returns b. When it returns b, what is b passed on as? It's passed on here into the variable y, because f calls g of x and keeps it as y. After some point, f decides to print y, right? So the last def of b that was here gets first use as print y when b is coupled with y. Here again, I don't consider this return statement as the first use of b. So going back to the definition, what does LastDef say? LastDef says that a variable x has a def clear path from the node through the call site to a use in another module. Now this can be of two different kinds. It can be from a caller to a callee, or it can be from a callee back to the caller. We saw examples of both these cases, right? So here if you see, this is from the caller to the callee. This LastDef x is equal to 14 is from the caller to the callee. This LastDef for b being 42 is from the callee back to the caller. So two kinds of LastDefs can be there. Similarly, what is first use? First use, the set of nodes that have uses of variable y for which there is a def clear and a use clear path from the call site to the nodes, right? So there is a def clear and a use clear. So if you see here, I have marked the first uses also, because once this last def happens, this is the place where it's first used, and in between we assume that there are no further definitions or use. One thing to note is that this calling and return at the call site doesn't constitute a part of the definition of LastDef or first use. So just a few more examples before we move on. So here is another piece of code. I have depicted it differently this time. So what we have shown is not as boxes like this containing the caller and the callee modules. What I have shown is I have shown it directly along with the control flow graph of the caller module and the callee module. So the one that you see on the left hand side here, x is equal, which are vertices labeled with 1, 2, 3 and 4. This is part of the caller module. B is the caller module, right? And this module is a caller module. The callee module is B. The variables that are coupled are x and y. B runs. Maybe there is an if statement here. One of these happens and then it prints y, right? So what are the last definitions? Last definitions for x could be either at node 2 or node 3 based on what the decision of this statement is. And what are the first uses? Not at the call site, please remember that. It's either at 11 or 12 based on what this condition is. So is this clear? So moving on, we had 3 data flow coverage criteria that we defined for call graphs. What were the 3 data flow coverage criteria? If you remember, they were all defs coverage, cover every definition to at least one use. Then it was all uses coverage, cover every definition to every use. And then the third was all DU paths coverage. From every definition, take every kind of path to every use. So I retain the same definitions. Instead, I look at coupling variables. So what is a coupling DU path? A coupling DU path is a path from not any f def to any use, it's from the last def to a first use. So I am in a situation where my code is fragmented into two modules. One module calls another module. So in the caller module, there is a place where last definition of a variable happens, and in the callee module, there is a place where the first definition of a variable happens. Then this pair is what is called a coupling pair. Here x and y is a coupling pair. So what I do is I take coupling du path as a path from last def to first use. Once I have coupling du paths, I take the same definitions of data flow coverage criteria that we looked at earlier and consider the same definition, but instead of considering it over all du paths, I consider it from last def to first use. So all coupling def coverage is a path to be executed from every last def to at least one first use. All coupling use coverage is a path to be executed from every last def to every first use. All coupling du paths coverage says that execute every simple path from every last def to every first use. Right? As always, you do best effort touring. So whenever I have to meet this data flow coverage criteria, if I have to do a side trip or a detour, I can do that to be able to make these test requirements satisfiable. Of course, the one requirement that I have about side trips to repeat is that side trips have to be definition clear, right? So what we will end today's module with is I'll explain to you through one full code example how data flow coverage criteria works. So here is the program that we will look at. So this is a Java program to compute the quadratic root of two numbers, right? So I assume that you have an equation of the form ax squared plus bx plus c, right? And I want to be able to compute two values for x. The standard formula says that x is given as this formula, right? Root 1 and root 2. So how does the code? The code has a class called quadratic. There are two variables which are floating point numbers, root 1 and root 2. What are x, y and z? These are the coefficients of the polynomial. Let's say ap squared plus bp plus c. A, b and c are the coefficients, so I pass them as x, y and z. And then I have this Boolean entity called ok, which basically tells me whether this polynomial has a solution or not. And then what I do is I take these parameters. Suppose I don't pass them as normal integer coefficients, then you just assign some default values. In this case, we've done 10, 9 and 12. And then you call this function method called root with these as parameters x, y and z. So root is the main method of this class quadratic that computes the quadratic root. So root returns this value OK, which says basically whether the quadratic roots have been computed or not. And if they have been computed, it is stored in the variables root 1 and root 2. So if OK turns out to be true, the values of root 1 and root 2 are printed. If OK turns out to be false, the value is what is printed is to say that this equation has no solution, right? So what is the focus here? Remember, the focus here is to be able to look at interfaces. So where is the interface? The interface is at this statement. This is the call site where this main quadratic class calls a method root with three formal parameters x, y and z, which are the coefficients of the quadratic equation that I am considering. So now we'll look at the code for root. What happens? It takes as input three positive integers, which are the coefficients, and it finds the quadratic root, right? So these are the three. So x, y and z, which are formal parameters here, are passed as actual parameters a, b and c. So what is coupled with what? X is coupled with a, y is coupled with b and z is coupled with c, right? And then it uses the standard formula that it computes for computing the quadratic equation. So here what it computes is an intermediate value, which is b squared minus 4ac. You can look up for how to solve quadratic roots. This is a standard formula to solve an equation of the form ax squared plus bx plus c. So if I compute b squared minus 4ac, then one solution is given as minus b plus square root of b squared minus 4ac by 2a. That is what is this. The next solution is given as minus b minus square root of b squared minus 4ac by 2a. D computes b squared minus 4ac. If d is 0, then there is no solution to the quadratic equation if d is less than 0. If d is greater than 0, then I can compute the two roots. So what we do is we first compute b squared minus 4ac and check whether it's less than 0. If it's less than 0, then this procedure, this method root, stores the result as false and returns the result. Otherwise, it computes these two square roots, stores it as root 1 and root 2, sets result to be true and returns the result. So how is the return passed here? Return is passed and assigned to this Boolean variable OK. If you remember, OK was a Boolean variable. So return is passed and assigned to this Boolean variable A. So what if OK is true? If OK is true means what? That I have computed root 1 and root 2, store it in these two variables. That's how I returned the result as true across these statements. If OK was false, then I have returned false, which means I haven't been able to compute the square root. So the system correctly prints. So what is the goal now? The goal is there is this main class which calls this method root. Root computes the root basically checks if the given system of equations has a solution or not based on the value of d. And if it doesn't have a solution, it says returns false. If it has a solution, it outputs the two roots, right? I want to be able to apply the data flow coverage criteria that I learned now in this lecture to be able to test this. So what are the things that we have to first do? We have to first identify the LastDefs and FirstUses. So which are the shared variables? If you see, root 1 and root 2 are the two shared variables. Which is the actual parameter that's passed and returned? OK is the parameter that is x, y, z are the parameters that are passed. Result is the parameter that is returned. So which are the LastDefs? LastDefs can occur at lines 10, 11, 12 or at lines 14, 15 and 16, which basically declare and initialize the three variables x, y and z. So we'll go back to the code. If you see lines 10, 11 and 12, take x, y and z as input. If it's some unacceptable value that is given as input, it sets its own values for x, y and z as some fixed constants in line 14, 15 and 16. After this, it's directly passed to this called method root. So the LastDefs for x, y and z are at lines 10, 11, 12 or at lines 14, 15 and 16. And when they are passed, x, y and z is coupled and with a, b and c respectively, right? And then what else is passed? Result. If you see, result is computed as false at line 31 or as true at line 36. So it's passed here. And then lines 34 and 35, if result happens to be true, compute root 1 and root 2. Lines 34 and 35 compute square root 1 and square root 2. Which are the first uses? Result is returned as OK in line 17, right? And x, y, z are passed as a, b, c, right? We saw this. Now, what are the coupling DU pairs? As I told you, x is coupled with a, y is coupled with b, z is coupled with d. Main method calls the root at passes x, y and z, takes x, y and z as input in lines 10, 11, 12 or at lines 14, 15, 16. Wherever they are taken as input, they are passed as a, b and c respectively at line 28. So read this as which is the method that is using it, which is the actual variable name, what is the statement number. That's what I've given. Method, variable name, statement number. Method main calls method root at line number 10 by passing formal parameter as x and actual parameter as a, where a is used at line number 28, right? And so on for the other things also. Method root returns back the value of root 1 to main, which is used by main at line number 19. This must be the print statement. Yeah, this must be the print statement of the method main. Similarly for result, which is coupled with the variable OK in the main variable, right? Once I do this, then I can normally write my data flow coverage criteria, all defs, all coupling defs, all coupling uses, all coupling DU pairs. I have not written the TR and the test cases for data flow coverage criteria in this case because this particular example code doesn't have any errors, but you can go ahead and do it as a small exercise for yourself. Write down the test requirement and give a test path that will satisfy the test requirement for coupling DU pairs coverage. Now, I hope this example would have clarified some details about how to use integration testing across parameter passing and shared variable interfaces to be able to test for data flow coverage criteria. Just a few other additional points that I would like to mention about data flow coverage criteria. One is when we look at data flow coverage criteria, even in the examples that I showed you, if you see, I sort of didn't give you the pieces of code that really didn't matter to us. If you go back to this slide, the rest of the code I put it out as ... right? So why? Because our focus is mainly on the values of the variables that are used or defined in the call. We really don't look at other DU pairs when we are focusing on interface integration testing. Right? The other thing we need to consider, which this example didn't illustrate, is that in languages like Java and C, there could be an implicit initialization of class or global variables, right? These implicit initializations will also have to be considered as definitions, even if they don't come as explicit defs or statements in the code, right? One more thing that I would like you all to note is that suppose you had this kind of a situation. A method A calls a method B, B in turn calls C, and let's say there is a variable that is defined in A and used in C. So this is what is called a transitive DU pair, right? It goes down a callee hierarchy. The kind of analysis that I have explained to you in today's lecture will not suffice to do this kind of call graphs. So you need slightly different kinds of analysis for that, and that we will not deal with in the scope of this course. So if you have to do this kind of analysis, I would say that you change the code a little bit to make method A use method B's variable directly, couple them with, and B and C's variable you couple it. Avoid coupling A and C variable. I'll point you to some papers at the end of this lecture where you can read up some more information about this, but the kind of analysis testing that we did today will not work for transitive pairs, right? And the other thing is that whenever you look at arrays, if I have to pass an array as a formal parameter or an actual parameter, how will I give? There, the interpretation that we take is a reference to one element in the array is considered as a reference to an entire array. I would also like to mention one important point. Data flow kind of testing that we saw today, which is coupling data flow criteria, is very important when it comes to certifying testing safety critical software. If you remember right in the first week, I told you that there are several standards and several standards that test for safety critical software. What are safety critical software? Software that flies our planes, drives our cars, controls nuclear power plants, maybe the software that runs metro trains across the metros of India. Because if there is a failure in the software, it can mean life-threatening loss or damage, right? So these safety critical software go through certification standards, which is what we discussed in the first week. One example of a certification standard that explicitly mentions coverage criteria is the standard DO 178C. It is used by Federal Aviation Authority in the USA, and in India also. Several of the DRDO firms used 178C as a reference for testing avionics application. In that, if you go to the standard, look at page 33, this particular section, it explicitly mentions to test for coupling data flow analysis, which is what is the kind of testing that we looked at today. So it says analysis should confirm the data coupling and control coupling between the code components. So it asks you to do testing and provide evidence of the fact that you've tested the interface for both structural coverage and data coupling. So here are some papers where you can read up for more information. This paper by Harold and Rothermel is considered the first place where this coupling and data flow testing across coupling was introduced. And this paper by Jin and Offutt is the paper that you should refer to for explicit first time introduction of the term LastDef and FirstUses. Thank you. What we will do next module is to be able to look at specifications and see how graphs are used for specifications. Thank you.